When you write code, it feels sequential. One line runs, then the next, then the next. But inside a modern CPU, execution is not strictly one instruction at a time from start to finish. Instead, multiple instructions are in progress at the same time. That is possible because of something called a pipeline. In this video, we're going to explain what a CPU pipeline is, why it exists, how it works, how it connects to instruction dispatch and branch prediction, and why pipelines are essential for modern processor performance. Let's begin with a simple problem. Imagine a processor that executes instructions in 3 steps. First, it fetches the instruction from memory. Second, it decodes what the instruction means. Third, it executes the instruction. In a very basic processor, those 3 steps would happen one after another for each instruction. Fetch instruction 1, decode instruction 1, execute instruction 1, then move to instruction 2. That works, but it wastes time, because while instruction 1 is being decoded, the fetch hardware is sitting idle. While instruction 1 is executing, both fetch and decode hardware are idle. The processor has multiple functional units, but they aren't being used efficiently. A pipeline fixes that inefficiency. Instead of finishing one instruction completely before starting the next, the processor overlaps the stages. While instruction 1 is being decoded, instruction 2 is being fetched. While instruction 1 is being executed, instruction 2 is being decoded, and instruction 3 is being fetched. Now, instead of completing one instruction every 3 cycles, the CPU can complete one instruction per cycle once the pipeline is full. This is the key idea. A pipeline increases throughput by overlapping instruction stages. It doesn't necessarily make a single instruction faster. It allows more instructions to be processed simultaneously. Let's make this more concrete. Imagine a simple 3-stage pipeline: fetch, decode, execute. In cycle 1, instruction A is fetched. In cycle 2, instruction A is decoded while instruction B is fetched. In cycle 3, instruction A is executed, instruction B is decoded, and instruction C is fetched. From that point on, every cycle completes one instruction. This overlapping structure is the pipeline. Modern CPUs have pipelines far deeper than 3 stages. Some have 10, 15, even 20 or more stages. The deeper the pipeline, the higher the potential clock speed, but deeper pipelines also introduce new challenges, because pipelines assume that instructions flow smoothly from one to the next. And software is not always smooth. There are hazards. Let's talk about the 3 main types of pipeline hazards. The first is structural hazards. This happens when 2 instructions need the same hardware resource at the same time. For example, if 2 stages both require access to memory and there's only one memory unit, one of them must wait. Modern processors are designed to reduce structural hazards by duplicating resources where possible. The second type is data hazards. This happens when one instruction depends on the result of a previous instruction. For example, suppose instruction A calculates a value and stores it in a register. Instruction B uses that value immediately afterward. If instruction B reaches the execute stage before instruction A has finished producing the result, there's a dependency conflict. The pipeline must either stall or use special techniques like forwarding, where intermediate results are passed directly to later stages without waiting for full completion. The third type is control hazards. These are caused by branches. When the CPU encounters a branch instruction, it may not know which instruction to fetch next. But the pipeline needs to keep fetching instructions to stay efficient. This is exactly where branch prediction becomes critical. Without branch prediction, every branch would force the pipeline to pause until the condition is resolved. With deep pipelines, that pause becomes extremely expensive. If a pipeline has 15 stages and a branch is mispredicted, the CPU may need to flush many partially processed instructions. All that work is discarded. This is why branch prediction and pipelines are tightly connected. The deeper the pipeline, the more important accurate branch prediction becomes. Now let's connect pipelines back to instruction dispatch. In the instruction dispatch model, we said that the CPU repeatedly selects the next instruction and executes it. In a pipelined processor, dispatch still selects instructions in order, but internally, those instructions are broken into stages and processed in parallel. Dispatch feeds the pipeline. The pipeline keeps execution moving, and prediction keeps the pipeline full. Now let's talk about something important. Pipelines improve throughput, not latency. Latency is how long a single instruction takes from start to finish. Throughput is how many instructions complete per unit of time. A pipeline might not make one instruction complete faster, but it allows many instructions to complete back-to-back much more efficiently. This is similar to an assembly line in manufacturing. If you build a product step by step alone, it may take 10 hours. If you create an assembly line, the first product still takes 10 hours. But once the line is full, you might produce one finished product every hour. That's throughput improvement. Now let's explore why deeper pipelines became popular. As engineers tried to increase clock speeds, they broke instruction processing into more stages. Smaller stages can run faster. But breaking work into more stages increases the penalty of disruption. If something goes wrong, like a branch misprediction, more partially completed work must be discarded. So modern CPU design is a balance. Deeper pipelines allow higher clock speeds, but they increase misprediction cost and complexity. Now let's talk about pipeline stalls. A stall occurs when one stage of the pipeline cannot proceed. For example, if an instruction depends on data that is not yet available, the pipeline may insert bubbles. A bubble is an empty cycle where no useful work is done. Too many bubbles reduce performance. Processors use techniques like forwarding, reordering, and speculative execution to reduce stalls. Forwarding allows intermediate results to be passed directly between stages. Speculative execution allows the CPU to execute instructions ahead of time based on predictions. Out-of-order execution, which we'll cover in another video, allows the CPU to rearrange instructions internally to avoid waiting on slow operations. But at its core, all of this complexity exists to keep the pipeline busy. An idle pipeline is wasted performance. Now let's address a common misconception. Many people imagine that a CPU executes one instruction at a time in a neat sequence. In reality, at any given moment, multiple instructions are in different stages of execution. One might be in fetch, another in decode, another in execute, another in memory access, another in write back. All simultaneously. The pipeline is like a flowing stream of work. Another misconception is that pipelines guarantee speed. They do not. They increase potential throughput. But hazards, mispredictions, cache misses, and data dependencies can all reduce actual performance. That's why performance analysis often focuses on reducing pipeline stalls and improving branch predictability. Now let's connect pipelines to the bigger picture of software execution. You've already learned about entry points, startup semantics, instruction dispatch, branch prediction. All of those mechanisms feed into pipeline efficiency. Entry points determine where execution begins. Dispatch determines what instruction runs next. Branch prediction guesses control flow. The pipeline executes many instructions at once. All of these layers work together to make modern processors fast. Without pipelines, processors would be dramatically slower. Without prediction, pipelines would constantly stall. Without dispatch, there would be no structured execution flow. So when you write code and your program runs instantly, you're benefiting from a highly optimized pipeline that is constantly overlapping, predicting, forwarding, and coordinating instruction flow at incredible speeds. Understanding pipelines gives you a clearer mental model of how performance actually works. It helps explain why predictable loops are fast, why unpredictable branches hurt, why tight dependencies can slow execution, and why modern CPUs are engineering marvels. At the most fundamental level, a CPU pipeline is simply this: a structured way of overlapping instruction stages to increase throughput. It is one of the core ideas that make high-performance computing possible. And it is a critical piece of the software execution model. In the next step of this series, we can explore out-of-order execution, how processors go even further by rearranging instructions internally to maximize pipeline utilization. But for now, you can think of pipelines as the engine that keeps instructions flowing smoothly through the processor. They are the invisible assembly line behind every line of code you run.